Do you think we are good drivers?
We have learned the physics of driving and are going to prove to you that you can trust us driving.
So there's no need to worry about us when we are driving.
Good driving involves reaction time. While driving, reaction time is affected by conversations with other people in the car, multitasking, eating, changing the radio, talking on the phone, and texting.
In class, we did an experiment about texting and driving. Average reaction time was 0.24 seconds slower while texting.
Other factors that affect reaction time are drugs, alcohol, medication, age, gender, tiredness, and experience. Reaction time is the time it takes for you to react plus the time it takes for you to complete the action.
You cannot change your reaction time, but your reaction time dictates your stopping distance. That is the distance from when you see something, apply the brakes, and the car stops. The higher the velocity makes the distance you travel before you touch the brake longer, making your stopping distance longer. If you are speeding, you need more reaction distance.
As the speed of the car increases, so does the braking distance. Braking distance is the time from when you apply the brakes to when your car actually stops moving. One would think that the speed doubles. The braking distance would double as well, but this is not true. Doubling your speed will quadruple your braking distance. For this reason, obeying the speed limits posted on the roads are very important. For example, we found in our lab when the speed was 5 miles per hour, the braking distance is 2.5 feet. When the speed is doubled to 10 miles per hour, the braking distance changes to 9.7 feet. This does not seem like a huge distance, but the speed limit is set at 25 miles per hour, and if you go 30 minutes instead, you're increasing your braking distance by 26 feet.
Total stopping distance is the reaction distance plus braking distance. The greater the speed, the greater the reaction distance. Reaction distance is the time from when you see something to when you apply the brakes, and like we said before, braking distance is the time from when the brakes are applied to the time the car stops. These two variables put together creates total stopping distance.
You need to be aware of what is going to happen while driving before it happens. Estimates help you figure out the safe following distances. You need to leave yourself enough room to react to what the car in front of you does.
An object in motion stays in motion. An example would be the lab with bowling ball and broom and circle in class. Applying a force to the object aimed in the direction of the center of the circle makes the object travel in a circle. When turning, a force is acted upon it, and during a turn you are accelerating. Since you are accelerating when turning, this means that your speed changes, direction changes, and/or both change. The greater the velocity or speed, the greater the acceleration. A fast-moving car needs more friction to keep turning. If speed is too large, the road surface and tires may not be able to supply force. Centripetal force is proportional to the velocity, implying that doubling the speed will require 4 times the centripetal force to keep the object in motion in the circle. If the centripetal force must be provided by friction alone, like driving a car on a curve, an increase in speed could lead to an unexpected skid if friction is insufficient.
The yellow light model is what is used to design a safe intersection. A safe intersection is dependent on the fact that the go zone is greater than the stop zone and that these zones are overlapping. First, the variables that affect an intersection are speed limit, width, reaction time of driver, braking, acceleration. These factors help traffic organizers to plan how long the yellow light should last. The size of the go zone and stop zone depends on the design of the intersection as well as safe operations of the car. All intersections are designed to be safe, but it is the driver in them that can make them unsafe. If you feel that a yellow light is too short, that probably means that you are over the speed limit. Different factors affect the go zone and stop zones. We found this through our yellow light lab.
The go zone includes everything in front of the stop line where the car can safely, without speeding, make it through the intersection when the light turns yellow. The go zone depends on the car's speed, time of light, and width of the intersection. Go zone increases if time of light increases, go zone increases if speed increases, and go zone decreases if intersection is wider. If the driver is speeding, then the go zone becomes smaller, and therefore they may not make it through the intersection in time, resulting in a crash.
The stop zone lies beyond the stopping distance of a car. It technically stretches infinitely. The stop zone is dependent on the speed, reaction time, and braking acceleration. The stop zone increases as the speed decreases. Stop zone decreases if the braking acceleration increases and the stop zone increases if reaction time increases.
That the yellow light model works. If the stop zone is equal to the go zone, the zones do not overlap, therefore there is a gray area where the car has neither enough room to stop or go. If the go zone is less than the stop zone, there is also a gray zone where the car has neither enough room to stop or go. When the go zone is greater than the stop zone, there is an overlap part where it is okay to stop or go. For every 5 meters that the go zone is greater than the stop zone, that represents one car going through a yellow light. Clearly, it would be impractical for cars to go through a yellow light, so the go zone is typically greater by 10 meters, meaning that 2 cars can make it through the yellow light.
Now we prove to you we understand the physics of driving and we can take the keys to the car.